Okay, so today, before we start our lab session, I want to have some kind of review, right, on what we learned so far, right? I know there's quite some quite some derivation, but let's actually review what we did, right? What we did. So in this in this in our originally we get the equation. We get the equation. This is the amplitude, right? Okay, so we have the A omega. We need to first shift the carrier frequency, right? We shift the carrier frequency. So what we have is the A bar omega, right? What we have is A bar omega. This is a review. Everything I said here is already appeared from your previous note. If you want to just look up previous notes, that's fine. You don't need to write it down because everything is the same, right? So, okay, so we have this U bar dt is the d omega 2 pi A bar omega minus omega naught, right? So this is the in frequency domain, right? So this, but now it's being shifted. And then exponential I k omega minus k naught, right? K naught z minus I omega minus omega naught t, right? So that's the Fourier transform, right? That's the Fourier transform. So we're going to have this capital omega as omega minus omega naught. And then we have the k omega as k, right? K omega naught plus, it's being shifted, right? So k omega is the k omega naught plus this. So basically, this is our k capital omega, right? So then we have k omega naught plus omega, right? So omega naught plus omega is omega naught plus capital omega is this omega, right? So this piece, this number is this number minus k naught, right? So we replace this piece by k capital omega, right? So this capital omega is the new axis on the shifted figure, right? So then we have k Taylor's expansion. We have the k naught omega prime capital omega plus half k naught double prime omega square plus 1/6 k naught triple prime omega third, right? So if you want to ask what is the k naught double prime, what is the k naught double prime? So the k naught double prime is the derivative, right? Is this derivative? So I'm going to show you that's the second derivative of the k, of this k. What is k? K is n omega c, right? So k naught double prime is the second derivative of this k omega, right? What is the k? K omega. K omega is n omega over c, right? That's the homework. This is the homework, right? So you just take the second derivative, right? You just take the second derivative. So I'm going to explain later on, but any questions so far? Okay, so with that, we've gone through the Taylor's expansion, right? use this Taylor's expansion, put it into here. We carry out the Taylor's expansion, and then each of this I omega, right? I omega or omega square. If you do the Fourier transform, it is d dt, right? If you look it up, it's d dt. So we end up with an equation that, because each one is I omega, is here is a derivative with respect to t. So this equation becomes, we can derive this equation, and this equation becomes the, skipping a few more steps, ut, right? U I z zt minus half k naught double prime partial u partial t square zt. So the second order term minus I over 6 k naught triple prime partial u partial t third derivative zt, right? We can write more terms, but this is at least for our class, this is the maximum we will go, right?
Dr. Hu,
Yes.
is that missing the first term, like the k naught prime term?
Yeah, okay. So the first term, it was there, but we proved that the first term is actually the propagating term, right? Remember, I give you an analogy, an example. If we have this term as the partial u partial t, zt is negative k naught prime partial u zt over partial t, right? So this is a propagation term. This is a propagation term. It is representing a pulse propagating without changing the shape, So if we change the parameter, if we switch the parameter using the t prime as the t minus k naught prime z and the z prime as z, this term disappeared. So basically, if we change variable, this term disappeared, and we got that. So
all right, thanks.
Yeah,
I caught up in my notes now.
Okay, thank you. Yeah, but it's good that you're not the only one got confused. When I learned this material, I got confused too. So basically, what we have this t, it should be all primed, right? It should be all primed. But for the simplicity, let's just remove the prime. So just everything to be, everything to be more simple, simplified version, right? Thanks for asking. So that derived, and we removed that, and we got this equation. Right? Thanks for asking. I always encourage everyone to ask questions, because if you have a question, chances are that your classmates will have the similar question. So if you ask this question, do everybody a favor, right? And also do me a favor. Sometimes I probably skip some steps. Okay, so with that, now let's only look at this piece. So this is high order dispersion term. We will come back later on. But for now, let's just look at this piece, right?
Professor?
Go ahead. Questions?
I think Josiah is trying to get into the class. Oh, wait, maybe he just got in.
I got in. Thanks, Ben.
Yeah. Yeah, thank you. I just got him in. So, but luckily I actually, I saved, I record all the video, so you should be able to watch it later on. Oh, by the way, I upload all the video online. So I've uploaded the video, all the video online. So if you missed any of the material, please go see the video. Okay. Okay. So now we look at this piece, right? We look at this piece, and if you look up on your notes, right? You look up on your notes, it's the DDZ, right? DDZ. So it's K minus K naught prime. So that is the derivation. Let me take a look also. I mean, I need to remind myself too. DDZ, yeah. So we will take a Fourier transform. So we take a Fourier transform here, we take a Fourier transform here, and then what we have is the ddt will give me the second derivative, right? So this will give us this will give me the omega square, right? Remember the derivative at h1, we take a derivative, and in Fourier domain, it's basically omega. So what we have is, let me see, did I have the, where is the equation? So bear with me, it's a lot of notes on my stuff also. So that's the, yes. So you end up with Z as you get, oh yes, okay, yeah. So basically this is the, if we are all put together, basically if we include all the terms, right? If we include all the terms, this is basically what we have as the I K naught, K minus K naught is I omega, K naught double prime omega. Yeah, okay. So let's take a look. The equation basically is this, right? Is this. So if we take a Fourier transform, this DDZ, right? So DDZ, and then we take a Fourier transform, the U tilde Z omega partial Z I, and equals on the right hand side, it's K naught double prime over 2, right? And then we take a Fourier transform, it's omega square, right? It's omega square. And then we have the U tilde U Z omega, right? U Z omega. And then we will put the DZ over here, right? We move the DZ on the right hand side, and we move the U Z omega to the left hand side. And then this will be the nature log. This will be the nature log. And then the result is the, let me directly write it down, as the result is this, what is this? It's the second, yeah. So U tilde Z omega is U tilde 0 omega times the exponential I K naught double prime over 2 omega square Z, right? Omega square Z. Okay, so I think there is a negative sign here because it's I omega. It's the I omega, so there is a negative sign. Yeah, so your I move over there, it's positive. Okay, so that's the equation, right? That's the equation. Basically, this is the equation for the propagation in the frequency domain. Okay, questions? Okay, then we introduce our for this square, right? We got that, we got this, we got that. This is u 0 t u 0 omega tilde u z omega tilde u z t. Right? We got this. So in this case, we need to first do the Fourier transform. We need to first take the Fourier transform, then we will do propagation, then we take the Fourier transform back. We take the Fourier transform back. Right? We take the Fourier transform back. Okay. Okay. So let's first have this Fourier transform. We have this u0t. This is demo, right? This is demo. So u0t is the a exponential negative t squared over 2t naught squared, right? So in this case, it is a exponential negative t naught squared over the. So this is the Gaussian pulse. This is the Gaussian pulse. The width is determined by t naught. Width is determined by t naught, right? So then this is the field. This is the field, and then the power is absolute value square, right? So what we have is a square, and then take the square. It will be negative t over t naught square, right? So that's the power, right? Power. So we're in the power 4 with half maximum, right? 4 with half maximum. That's usually how you quantify a pulse. That's how you quantify a pulse, right? We take the half of the half maximum, and then we take the 4 width. So this is our pulse width, right? So in other words, we put this t, right? T4 with half maximum and over 2, right? U0 here. So T4, this is T4 with half maximum. So we take half of it, which is this chunk, right? So half of it, this should be the half of the maximum. So it should be half of the maximum. So this U should be the half of the maximum, right? So what is the maximum? It's 0, 0, right? Once you actually at 0, it's the maximum, right? So then you put it there. What we can get is a square, and you put the T4 with half maximum in it. Negative T4 with half maximum over 2 square T naught square is, right, is half of the A, and 0, 0 is 1 square, right? Square. And then use this equation, we can get the relationship between T4 we have maximum and T naught, right? Because this portion is the natural log of half. So use that, we can get the T4 we have maximum, right? We can represent the T. So for example, if I want the 4 we have maximum as 1 picosecond, then we can have this is 1 picosecond over 2 square over T naught square is basically natural log half, right? So you can have this relationship. Questions on this? Okay, now then we will actually in the frequency domain, right? So we'll simply take a Fourier transform. We'll take a Fourier transform, and our Fourier transform, this is the U0t, right? And we take a Fourier transform, what we have is U tilde 0 omega, right? This U tilde 0 omega is square root of 2 pi A naught, right? A naught exponential negative omega T naught square 2, right? So in this case, we can write down the same thing. So this is now T naught is a constant. So it's a frequency function, right? As a function of omega. So we'll do the same thing. We will write down as exponential negative omega 4 with half maximum over 2 square T naught square over 2, right? Because we need to actually take the square, right? So this absolute square is going to be half, right? It's going to be half because the 4 with half maximum, right? So in the 4 with half maximum, this is omega, right? So if this is omega 4 with half maximum over 2. This is the half here, and this piece, take a square, it should be half, right? That's how you calculate, right? So now you can find out the omega 4 with half maximum is something related to the T naught, right? Something related to the T naught. So you go back and find out the answer, right? Related to the T naught. And then what in the first homework, what we need to do is to calculate this T4 with half maximum and the product of omega 4 with half maximum. So let me write it here. You may not, you should be able to see it. So the product of 4 with half maximum, right? So this is dependent on T naught. This is also dependent on T naught. You calculate, it will cancel out at the end, right? So that's, but one thing you need to pay attention is that this is omega. This is called angular frequency, right? Angular frequency. So omega is 2 pi f, right? So if you calculate frequency, you need to divide by 2 pi. And in the textbook, sometimes f and the nu represent the frequency, right? So this is the frequency, right? Omega is the angular frequency. So this is the frequency. Omega is angular frequency, right? So you need to actually make this conversion using the 2 pi, right? Okay, questions in this piece? Okay, so next, right? Next, let's look at, let's take a look, right? Let's take a look, and we have this dispersion, right? So again, everything what I said here is a review, right? So you can look it up from your notes. Okay. So K naught double prime, right? From here, it's the second leg. K naught double prime is K naught prime, right? D omega. And then this D dispersion parameter is the D K naught double prime over D lambda, right? So remember, this is the 1 over the velocity. So this is the 1 over velocity. So this dispersion parameter, the unit is picosecond per nanometer per kilometer, right? So meaning that if I propagate 1 kilometer, if the frequency space, the wavelength space is 1 nanometer, how much delay it will experience in picosecond, right? So that's the dispersion parameter, right? Okay, so then we have the, we also have the omega over c is 2 pi over lambda, right? Omega over c is 2 pi over lambda. Questions?
Yeah, I have a question. So on the units, is the denominator, is it nanometers times kilometers, or is
That's
it?
correct. So it's actually this.
Okay.
But this usually it's written as a dash.
But it is technically multiplied on the bottom.
Yeah, technical. So it's actually picosecond divided by nanometer kilometer. It's thanks for asking. It's actually better like this.
Would that reduce to microns on the bottom, or does, I mean, I know we wouldn't write it like that, but would that essentially just be?
Yeah, not micron square.
Okay.
Right? So let's do it, right? So it's 10 to the 9, negative 9 meter, 10 to the negative 10 to the positive 3 meter. So it's the picosecond. So it is 10 to the negative 6 meter square. So if you want to write it, it is the millimeter square.
Okay.
Yeah, you can write it in the millimeter square. But I usually, it's actually more understand in this way. The reason is that in the fiber propagation, usually quantified by a kilometer. In the bandwidth, it's usually quantified by nanometer.
Okay.
Yeah, so if you just give you a little bit more why we people look at the nanometer is because, you know, 600 nanometer is roughly like a red, right? 633 is red laser. You know, it's so I have my laser pointer, right? So yeah. So this one, the laser pointer is the 633 nanometer. So and the 400. Oh gosh, the 400 is the green or blue something. Yeah, 400 nanometer. It's a different nanometer corresponding to different color. Then if you have 1 nanometer difference, for example, 632 and 633 nanometer, these two laser, and if they, for example, if the unit is 1 picosecond, if the dispersion is 1 picosecond, 1 nanometer per kilometer, so 633, 36, 32, if they propagate by 1 kilometer, they are 1 picosecond apart. That's what 1 picosecond per kilometer, per nanometer per kilometer means. Okay, so thanks for asking, that's good. So that's the dispersion, right? This is the d omega. So that's the omega and the c and lambda, that's the relationship. Okay, we will add the d lambda in it, d lambda, d omega, d lambda, d k naught prime, right? D k naught prime. And then what is the k naught? K naught is n omega c, right? So d k naught prime over d lambda is this capital D. What is D? D is this, picosecond nanometer per kilometer. How much is d lambda over d omega? You can do this, right? You can take a derivative, it's d omega, and then d1 over lambda, you were going to have the omega, right? So let's do the d lambda, right? Let's take instead of lambda, we can take a derivative, right? So what we can do is lambda is 2 pi omega, 2 pi, oops. Now we move lambda to the left hand side, 2 pi c over lambda. right? Now we can take a derivative, right? So we take a derivative, so d lambda, right? We take a derivative. And d lambda and 2 pi c is a constant. D omega is omega, so d omega -1, right? And this is 2 pi c, take a derivative, so it's omega square, right? Omega square d omega. And then there's a negative, right? 2 pi c omega square d omega. So now we've moved the d lambda and d omega move to the left-hand side. What we have is negative 2 pi c over omega square capital D. Right? That's in your note also. Okay, so once we have with omega c is also omega over omega square here, omega over c is 2 pi over lambda. So we can write, we can use the lambda to represent omega, right? So it is negative lambda naught over omega, right? I shouldn't use lambda naught because I just use lambda. So it's negative d, right? We can also further write as lambda over 2 pi c d, right? So those are just simply changing the parameter between lambda and d. Okay. 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 So now what is the k double prime? What is the k double prime? Right? So k, let's say k omega is n omega over c. Right?
Dr. Liu,
Yes.
would the lambda be squared in the last equation you just wrote whenever you?
Yeah, you're right. Thanks. Because we removed the omega, that should be squared. Thanks for pointing it out. Yeah. Okay, great. So this is this typo. It should be lambda square. Thanks for pointing it out. K omega is n omega k is n omega over c, right? So let's look at what is k, right? K is propagation constant. So in the air, right? In the vacuum or in the air, so the k naught is 2 pi over lambda, right? K naught is 2 pi over lambda. Well, k, right? 2 pi over lambda. So in other words, we always see something like cosine kz, right? Minus omega t. Those are harmonic waves, right? What does it mean? Meaning that if I have a cosine wave propagating, right? This k is 2 pi over lambda. Z propagate by lambda. How much phase it changed? It changed by 2 pi. If the z propagate by lambda, so the phase change is by 2 pi. So cosine coming back, right? That's what this is called propagation constant. It's in the air, it's k naught is 2 pi over lambda, right? Is omega over c, right? It is omega over c. But if we have in glass, k is n 2 pi over c equals n omega over c. 2 pi over lambda, right? So n, right? Because it is by a refractive index. It's in glass, right? In glass. So it's the k in the glass is n omega over c. But this n is frequency dependent, right? It's the index is frequency dependent. Why? It's if you have a prism, right? If you're coming back and different color will have different direction, right? RGB. Because it's the index is different for different wavelengths. That's why you got you have prism. You can split the different laser light. If you come in with the white, and then you can spread out the RGB. So this N is omega dependent or frequency dependent, wavelength dependent, whatever you want to call it, right? So this N omega is K naught plus K naught prime omega minus omega naught. This is capital omega as we used, right? So plus K naught double prime omega minus omega naught square over 2, right? And then the higher order term. So this is the Taylor's expansion. So with this Taylor's expansion, we can, that's what we cover at the beginning. What is K naught prime? K naught prime is D, right? D N omega over C D omega, right? K naught prime is this piece, right? So we use the UV, right? So we take a derivative. So UV derivative is U derivative V plus UV derivative, right? We derivative U derivative V. So that equals the, let's first take a derivative of N, right? So it is the 1 over C is constant. So let's dN d omega, right? But we need to have omega over C. And then we take a derivative on omega. It is basically N, right? So that's the K prime, K naught prime. K naught prime is this piece. And C is pulled out. There shouldn't be a C. Right? Okay. Okay. So that's the dN d omega. Right? That's the K prime. So K naught prime, K naught double prime will take this on the another derivative, right? K naught double prime is d omega second derivative and omega over C, right? It's the second derivative. Second derivative is the derivative of the first derivative. And then we take another derivative here. Let me skip the step. I mean, you can do it by yourself, right? You take this and use the dN d omega, and then the simplification at the end, what you will get is 2 dN d omega plus omega dN square d omega square, right? Okay. 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 So if you want what you need to do in the homework, right? So in the homework we have a question that is the you need to find out what is the K. Proof D, we need to find out that D is the so D is this, right? D is d K naught prime d lambda, right? D K naught prime d lambda. And we want to find D, prove that this is lambda over C dN squared d lambda squared, right? That's what we want to find. Okay, so K prime is this, right? K prime is this. That's what we covered, right? Well, K prime is this. And then we will, let's replace d omega by d lambda, right? So basically you replace d omega by d lambda, just this equation, right? So this d omega is whatever, omega square over 2 pi c negative, just put it there, and then take another d lambda. Take another derivative on d lambda. You should get this result. Right? Any questions for this piece? It's actually in the notes. You just dk naught is this, and d omega replaced by d lambda, take another derivative of lambda. That's it for the homework, right? Homework 2. Okay. Questions?
Dr. Who,
Yes.
I've got one quick question.
Thank you.
I guess I'm a little confused because I thought dk or dk naught prime was equal to k naught double prime, as like we have at the top, that top line, or like the next line beneath it, right there.
Yeah. So k naught double prime is dk naught prime d omega, right? What's your? Can you repeat your question again?
So I guess why are we substituting k naught prime and not k naught double prime if d equals dk naught prime?
Okay. How about this? Why don't you write down what do you want to say here? What are you trying to say? Yeah. Just write down the equation. I'll write it down. Go ahead.
So like if we have dk naught prime over d omega, and that equals k naught double prime.
Yes.
So I guess why are we not using the k naught double prime equation to solve for d?
K naught double prime equation. Which K naught double prime equation?
The
This
one at
equation?
the very bottom line. Why are we then not using that equation to solve for d?
Oh yeah. I mean, you could solve this. It's just replace the d omega by d lambda. You should get the same result, but it's just more complicated.
Okay.
In other words, you have this K naught, right? So you have this. In other words, what you are saying is you are perfectly correct. So basically, you have this and you have that, right? So you K naught double prime and D has the relationship, and then this K naught is the same here. So basically, this is the same. You just replace d omega by d lambda. You should get the correct answer. You are absolutely correct. In terms of which one more complicated, it's personal preference. Either way is fine.
Okay.
Yeah, what you said is absolutely correct. Yeah. So basically, you use that and use this replace. You should be correct. Yeah.
Okay.
It's probably easier. It's personal preference, but at the end, you should get the same result.
Okay. Thank you.
Yeah. Great. Thanks. Okay. Great. That's actually homework number. The third homework is you just substitute the parameter, right? I mean, I want to just let you know why we bother, right? So in other words, usually it's people quantify by n lambda, right? N lambda. And then you want to say, with this n lambda, how much is the d, right? Although it's not, we're still, although this is class, we're not actually in the research scale, but at least you know why we, look at this problem. Okay, great. That's actually pretty much it, right? I mean, so this is the third leg, and once we get that, we got at the end, we have this equation, right? So we get this equation, it's the z over this t 4-wave half maximum is the original, right? So this is the TZ, right? Is the original 4-wave half maximum 0 times 1 plus z over LD, right? Square, take a square root, right? So after we take a final step, that's what we got, right? That's what we got. Basically, what is LD? LD is T naught prime over K naught double prime absolute value, right? So meaning that Z broadening is play a role once the Z is comparable with LD, right? If Z is way less than LD, it's almost the same as forward half maxima at the 0 point. But if the Z is in the 1 LD, right? 1 LD, in other words, now Z is in the 1 LD, Z equals to 1 LD. So the width TZ is 1 to square root of 2 T4 with half maximum 0. So meaning that once Z is propagated by 1 LD, the dispersion length, the broadening is multiplied by a factor of square root of 2, right? Factor of square root of 2. So that means it's if the Z is way less than LD, there's no change, right? Way is less than LD is no change. So let me ask, right? If I have a large T naught, that means I have a large T naught. That means I have a large LD. So in other words, if I increase the width of T naught, basically dispersion effect is less, right? If I increase the T naught, dispersion effect is going to be less. Why? Because the LD is, if T naught is twice, the LD is 4 times. So that means I need to propagate longer in order to have dispersion effect, right? Okay, so if my pulse is broadened, in my spectral domain, it should be half, right? So in other words, time domain and spectral domain is inverse. So the reason is that if my broadened pulse in time domain, spectral domain is half. So for the same fiber, we quantify dispersion as picosecond per nanometer per kilometer, right? So if we still propagate at 1 kilometer, if my bandwidth is half, right? Bandwidth is half. This dispersion, it play a less role, right? That's what we can use this simple LD, right? So my pulse is doubled, then dispersion length is 4 times, right? 4 times, quadrupled, and then I need to propagate more in order to see the dispersion effect. In frequency domain, it's because the spectrum is narrower. So the dispersion play a less important role here. Yeah. So it's all all together, right? I mean, I hope you can understand this concept. Yeah. Okay. Questions? Right? Questions? Yeah, I want you to understand this concept, right? I mean, and then this will be what if my K naught double prime is actually twice? Whether this dispersion, whether it's play a more important role or less important role. This might be a very good question for the final exam, right? So make sure you understand. This will be a good question for the final exam. If I remember, I'll put it there in the final exam, right? Why? What's the mechanism? Okay, so that's pretty much it, right? That's pretty much it. Okay, so we still have about 20 minutes, right? About 20 minutes. One thing I want to, I have quite, busy schedule, so I want to actually make one of the students is not available this Friday, so I want to move the class to the following Friday. So next class we have Monday, Wednesday, Friday, right? So it's Monday, Wednesday, Friday. So I need to finish, I need to finish class. So it's 10, 10 up to 10, 10 up to 10, 11, up to 11. And here it is also 10, 10 up to 11, right? Up to 11 a.m. Yeah. So I need to stop here at the 11 for those 2 days. And then as a way to compensate, I already record the video. We have a video. We have a video, so go back and watch a video. I think it's you go back and watch the video, and then for this class, we will have for those 2 classes, we will start from the I'll add back 10 minutes each. So we'll start at 10, and then we start at 10. Would that be okay? So on Monday and Friday, we start at 10 a.m. And here with so on Wednesday we start at 10, finish at 11. On Friday we start at 10, finish at 11:25. And do you have any conflict if we start at 10 a.m. on this coming Wednesday and Friday? Okay, if you have some time conflict, please let me know. And also, if there's any schedule change, I'll send you by email. But that's pretty much should be the changes, right? But on Monday and Wednesday, we'll finish at 11 o'clock. So I'll write an email so you can mark your calendar. I'll mark your calendar. Okay. Okay, great. Okay, so for the rest of thank you for your response. For the rest of the class, we will go to the lab session, and we will work together on the section 2, the lab session section 2. That's the MATLAB. That's MATLAB. What I'm going to the format going to be, now we are virtual. So you go ahead and run your code, and there is a comment, right? Basically, what you need to do is write down the equation, right? Write down the equation. That's this piece. So you need to write this comment: z omega is u0 omega, and exponential I k naught double prime over 2 omega squared z, right? So you need to write down this comment in the MATLAB and make sure what is k naught double prime, right? What is omega? This omega needs to be shifted, right? And that's the z. So you need to write down this, right? You need to write down this, this. Okay? Okay, you can download the file from Canvas. So go ahead. Yeah, so look for the file from the Canvas. And I'm here, and if you have a question, let me know. So let's work together. It's actually really hard. Sometimes if you, I mean, this is not like homework. If you don't know, go review the material. You will go look up the material. You can study by yourself. Sometimes if you stuck for 1 hour, you stuck for 2 hours, 3 hours, there's no progress. But I'm here to help you move forward. Yeah, please go back to the MATLAB, to the lab session. So I'll be still here.
Did you say that there was a file we could download on Canvas?
Yes.
I can't